So, to start off with, again, just a reminder of as we last time talked about gas speed and how the particles are bouncing around. Well, when those particles bounce into each other or into their container, that is a pressure. So the pressure is defined as a force exerted on a surface. So we started by talking about just the speed of the gases, how small gases are faster than others. However, when you take into account mass and speed, you get kinetic energy. Remember, temperature is the measure of the average kinetic energy of particles. That kinetic energy is going to show how forceful those contacts are with other things. So it shouldn't matter what gas it is at a particular temperature, which at the same pressure, it's the same amount. Now, I list some common units for pressure on this slide as well. Millimeters of mercury is probably the most common. However, if you listen to the weather report, they will report it in inches of mercury, because we're in America. We don't do metric in America. Atmospheres, ATM, is probably the most common, though, that we will be using. So atmospheres is abbreviated ATM. PSI, that's one that you should know if you have an automobile. And if you park outside this time of year, maybe there's a light that indicates, hey, your air pressure is low. You need to put more air in your tires. So then you need to go, either you have your own air compressor or you go to a gas station. Heck, the one that is over across from the new apartment buildings even has one where it'll fill it to the exact pressure that you want without even having a pressure gauge. PSI stands for pounds per square inch. That's another American type unit. But torr, which I have kind of in bold, is actually the exact same as a millimeter of mercury. So the two are kind of interchangeable. And then a Pascal is the last one, which often Pascal's so tiny you need a lot of them, so a kilopascal is common as well. On the very bottom, I show you that equality that 760 millimeters of mercury is the same as 1 atmosphere. And actually on the whiteboard, I have that equality written down as well, because on your AP equation sheet, they will give you that information. So you do not have to memorize that, because there is a good chance that you will have to, at some point, do a conversion with those two things. Again, the only other thing I would mention is how did they come up with that unit of pressure? Somewhat similar to what we're doing today, that what they had was a bath full of mercury, and then they had a glass tube inverted in it. And then that glass tube had mercury in it as well. So if this was all mercury here and all around, and actually I even have glass tubes because we are going to be working with these glass tubes at some point in this unit as well, where we can measure the volume of a gas collected and then do some other calculations with it. If there was no gas at all in this top section here, it would be a vacuum. So a space void of all matter is a vacuum. That means there's no pressure pushing this down. However, gravity can still play a role in this. The only thing keeping that column up in the first place is the air pressure on the outside. Because as air is pushing down on the surface of something, the only place it can go is up. So when on a weather report you hear, like I listen to NBC 15, so Charlie Shortino in the morning says, and the pressure, there's a low pressure front coming through. That means that there's going to be less push down, which means this column would fall a little bit because there's not as much forcing it up. So, and the pressure is rising, well, a greater push. They used to measure that column of mercury and be able to tell then what was the pressure in that particular time. Atmospheres, I think, is more because we're now in the digital world, so we're able to use that instead of a unit of pressure. But I wanted you to be aware of what pressure is in those different units on this first slide. Again, kind of repeating myself so you don't have to write that down, and a vacuum is a space void of matter. we have a vacuum pump, and maybe I'll bring that out either at the end of class today if we have a little extra time, or beginning of next class, but the vacuum pump would try to get rid of all the air molecules possible. Outer space is kind of close to a vacuum, but even there they will have some parts as well. If we were to have a perfect vacuum, a space completely void of matter, the pressure would be zero. But again, we typically will not approach a pressure of zero, really, with anything. So again, my first couple slides just reminding you a little bit about pressure. We actually talked about vacuum in Chem 1. We probably did not do much with the units, however. And since we have to do a fair amount of math today, that's where I need you to be comfortable with these units, both how to use them in a calculation, how to convert from one to another as well. So Boyle's law is the first gas law that we covered in Chem 1. This was when we used the syringes. If you remember, we had like little marshmallows inside a syringe. You push in. Well, when you push in the plunger on a syringe, you're creating a higher pressure due to a lower volume. So Boyle's law is the inverse relationship between pressure and volume. Now, this is working if we have a flexible container. So if it's a rigid container, we're not going to be able to change the volume. But if we have something that we can adjust the volume, like imagine those syringes that we pushed in the plunger or pulled out this plunger, balloons can be considered a flexible container as well. You would see this relationship. Now, again, the one thing that we did not do in Chem 1 when you guys took it was introduce the mathematics behind it. This is the Boyle's law equation. P1 V1 equals P2 V2, where the 1s stand for like the initial pressure and volume, the 2's the final pressure and volume. This equation is not unit specific. And what I mean by that is the pressure could be given to you in millimeters of mercury. That's fine. Could be given to you in atmospheres. Could be given to you in torr. Like we give it to you in PSI if we want to. It doesn't matter. Kilopascal. Volume could be in liters. Could be in milliliters. Doesn't matter. However, it should be the same unit on both sides in order for you to do the algebra. Typically in a problem like this, you'll be given 3 of the 4 variables, then you solve for the 4th. Only thing that you have to do is keep things organized. So what I mean by that is sometimes students will, as they're reading a question, write down a P1 and a V1 next to things. Or they will annotate the question and highlight the numbers that they need to know. Again, the math department often suggests instead of plugging in numbers and then solving, first isolate the variable. And what I mean by that is if you were to solve for the final volume, you would say V2 equals P1 times V1 divided by P2. Again, that type of mathematics I focus on a little bit more with Chem 1 because they're a little bit lower level of math than you guys are. But as you're working today on calculations, if you have questions on that, let me know and I could easily show you that as well, or you can check my answer key. So we did talk about Boyle's law, but for you guys who didn't do the math, the other gas law that we did in Chem 1 was Charles' law. And this is another one that we talked about, but we didn't do the math for. But we're going to have you guys do that now. This is the direct relationship between volume and temperature. So this is where we did the can crushing. So we heated up our can, we put it in cold water, and it crushed. And what we said was, well, the temperature decreased, hot to cold, the volume decreased. Because if you think about it, if volume decreases, if temperature decreases, things are slowing down. Remember the packet that we worked on, a lot of what we did last time dealing with gas speed. If they're at a lower temperature, they are going slower. And if they're going slower, they don't occupy as much space. Now again, that's what we were trying to do in Chem 1 to show you. And honestly, it is a little bit more than just that because you do also have to deal with the fact that there is pressure involved. And that's what we're going to cover later on today. Looks like I had a clip that I'll show you maybe a little bit later after all this is done dealing with that. The gas law itself mathematically is V1 over T1 equals V2 over T2. Now, this gas law is a little bit unit specific. Now, next class, we're going to introduce a gas law called the ideal gas law, and that's completely unit specific. Volume can still be in liters, volume can be in milliliters, that doesn't matter. Temperature, however, has to be in the unit called Kelvin. Kelvin is the absolute temperature scale. One of the things that's given to you on your equation sheet, which I wrote up on the board, but I'm also going to put on this slide right here, is the conversion between Kelvin and degrees Celsius. So once again, we will be measuring in degrees Celsius. However, you need to put it in Kelvin in order to use Charles' law. If you think about it, if something was 0 degrees Celsius, if you plug that into Charles' law directly, you'd have 0 in the denominator, and the entire math department would freak out. You can't divide by 0. This avoids that. Well, but what if it's negative 273 degrees Celsius? Then it would be 0. Yeah, but you're never going to get to negative 273 degrees Celsius. Because 0 Kelvin is what's called absolute zero. Absolute zero is where molecules would no longer even be vibrating. Because temperature is a measure of the average kinetic energy of particles. And not even in laboratories have they been able to achieve 0 Kelvin. There's always some background radiation or heat that's making things move a little bit. And I can ask you guys to sit as still as possible, but you are going to be moving a little bit in your seat. And I like to think of you guys in your seats as the solid state of matter, the one of the least motion, but there's still vibration that's occurring. Okay, one last slide. Standard temperature and pressure, which is often abbreviated STP. This is given to you on the equation sheet as well. I have it written up on the board right now. Standard pressure is 1 atmosphere, which is the same as 760 millimeters of mercury. This is typically, if there's no high or low pressure front moving into the area, the pressure at sea level. Recall when you increase in altitude, the pressure decreases. We talked about this with why water can boil at a lower temperature recently as well. So the higher up in altitude you go, you are going to have lower pressure. If you go underwater deeper and deeper, it would be higher pressure at that point. Standard temperature is 0 degrees Celsius. Seems a little odd that it's that cold. That's not what I consider standard or normal. Even the periodic table isn't based upon 0 degrees Celsius. It's based upon 25 degrees Celsius, what they consider to be a little bit more room temper-ish. I mean, this room is more like 21 degrees Celsius, but. And again, this last thing you don't have to write down. There's a reason why we have standards. And that's because, and you're going to be standardizing our own data for the lab report that you do. I think in about 2 class periods we have a lab. We need to standardize measurements because pressure can vary from one room to the next, let alone from one city to the next. In fact, one of the bathrooms that I use, the door jiggles when it's shut because there's a difference in pressure inside and outside of that room. It's kind of annoying. So because of different pressures at different locations, let alone different temperatures, again, this room versus other rooms in the school are different temperatures. To compare results appropriately between 2 different locations, you need to standardize your data. And that's something we're going to talk about a little bit more when we do the combined gas law a little bit later in class. However, that is something that we have to be aware of, is these standard conditions and how things vary from the standard conditions. And what we will start to do is start working on how to standardize our data during the course of today and next class. But the combined gas law, as the name implies, really is taking what we've just done and putting it together. Now, when I went over Boyle's law, P1V1 equals P2V2, that's assuming that temperature remains constant, which when we did the syringes, things weren't heating up or cooling down, so temperature remained constant. When we do Charles' law, V1 over T1 equals V2 over T2, that assumes pressure remains constant. So the only thing that's affecting the volume would be the temperature. The combined gas law says nothing remains constant except for maybe the number of particles that are involved. So it still has to be a sealed container. Before we do that, there is actually one more gas law that even in Chem 1 we didn't cover. It's called Gay-Lussac's law. Two separate scientists, I think, at the same time came up with the same idea. That pressure and temperature are directly related if volume remains constant. And this is kind of like what happens in the air in your tires. Again, unless there's a significant drop in pressure, your tires in your car don't look that much different. So when the temperature drops, the pressure drops, which is why you get that indicator on your car in the middle of fall. I would not plan on us practicing this equation, but again, this equation goes with the other two equations to form what's the combined gas law. However, if we were to use this equation, temperature would be in Kelvin. So again, we have these three separate gas laws: Boyle's, Charles, Gay-Lussac's, all dealing with pressure, temperature, and volume, two of the three variables, assuming the third variable remains constant. And the reason why we have the combined gas law is because sometimes you don't have one of those three variables remaining constant. So that's kind of what we're going to wrap up with, is using all these variables. Only thing that remains constant is the number of gas molecules. And the equation, a little bit easier if I just write it instead of even putting it on here, is P1 V1 over T1 equals P2 V2 over T2. Again, temperature would have to be in Kelvin, but pressure and volume, the units aren't dependent at all with this equation. Only thing tricky about this one is you have 6 variables, 5 of which you'd probably be given. Although this is very common when you start seeing solve for the volume at STP. So here are the initial set of conditions. What would the volume be at standard temperature and pressure? Actually, one of the labs that we're going to be doing will use this equation for that exact thing. So really, the only difficulty with this equation, because again, I believe in your ability to do algebra, the only difficulty with this is keeping track of all the variables. And secondly, if you ever had to solve for temperature, whenever you're solving for a variable in the denominator, that's when things are a little more difficult with the algebra. However, that's where when the math department suggests isolate the variable, that would help you out with that. Now, I do have one more slide. It's just a practice problem. I could go over with you, or if you guys feel comfortable, we could just give you a little bit of time to work again, which is awesome. We okay with just doing some algebra? Okay, so you picked up on the way of the sheet with that. Let's work on that for a little while.